This is section 13.3, which is about concentration units. And at this point, you should be familiar with molarity, which is moles over liters. But as we move forward into the semester, then we need to express concentration in a few different ways. So without further ado, let's start with percent by mass. Okay? Percent by mass simply is determining how much you have of a given solute per 100 parts of the solution. So we are considering the entire solution and what fraction of that solution is the solute. So simply put, all you have to do is to take the mass of the solute and divide it by the mass of solution times 100, and that is your percentage. So how you read that? For every 100 grams of solution, for example, you will have so many grams of the solute. One useful relationship that we can use along with the percent by mass is that the mass of the solution, remember by the law of conservation of mass, the mass of the solution is going to be equal to the mass of the solute plus the mass of the solvent. So how do we use this percent by mass in a calculation, for example? So we are interested in determining what is the percent by mass of 285 grams of solution that contains 85 grams of solute, right? So one of the first things that you have to keep in mind here is that this solution, 85 grams of that solution is solute, okay, as expressed there in our problem. That means if your total mass of solution is 285, then you have 200 grams of solvent. Okay? So now, how do we calculate percent by mass here in this case? So percent by mass is going to be equal to your mass of solute, 85 grams, divided by the total mass of solution, which is this one right here, 285, times 100. Notice that the units here, grams and grams, cancel each other, so it's not quite that they are canceling because one represents grams of solute and the other one represents grams of solution, but in terms of mass, it's kind of adimensional. So the result for this calculation is 29.8%. Now how we read this concentration, 29.8%? What that really means is that for every 100 grams of solution, there are 29.8 grams of solute. Okay, so this is how you read a percent by mass concentration. Okay, that is the meaning behind that percent. Okay, another way that we can use to express concentration are the ppms, ppbs, and ppbts. Conceptually, they are very similar to a percent by mass. You are still using the mass of solute and the mass of the solution. It's just that you use a different multiplier. So for percent by mass, your multiplier is 100 or 10 to the power of 2. But for parts per million, parts per billion, and parts per trillion, you use a different multiplier. Okay, one thing that I want you to notice here is that in all of these three units, you are using the ratio mass of solute divided by mass of solution in all three of them. But the difference is the multiplier that you're using. For parts per million, you're using 10 to the power of 6 or 1 million. For parts per billion, you use 10 to the power of 9 or 1 billion. And for, I spelled a mistake. Parts per trillion is 10 to the power of 12 or 1 trillion. So here there was a mistake. This is ppb and this is ppt. Okay, sorry about that. The other relationships are still valid, meaning the mass of solution is still the mass of solute plus the mass of solvent. However, whenever you see these concentrations, ppm, ppt, and ppv, they represent very, very small concentrations, so the very little amounts of solute in that solution. So that means that the amount of solute, the mass of the solute that you are going to have in these solutions is so small that most of the time they actually don't count. So the mass of solute is really small compared to the mass of solution. Therefore, for this, when you're using these concentrations, more likely the mass of the solution will be approximately equal to the mass of solvent. So the mass of solute doesn't count. So let's see that in a problem. So the EPA maximum contaminant level for mercury in drinking water is 2 ppv. Okay? And well, we want to know how many milligrams of mercury are contained in a glass of water, assuming that that glass of water is 250 milliliters at that concentration. So you have a glass of water, 250 milliliters, 2 ppv concentration. How much mercury is contained in that glass of water? So things that we have to assume here, well, we have volume, and ppv requires mass. Therefore, since this is water, this is pretty much equal to 250 grams. Okay, because density is equal to 1 gram per milliliter. Okay, so now this is 2 ppv, right? If we read this as we were reading the percentage, remember a percentage is how many grams per 100 grams of solution. In this case, it's how many grams of solute per billion grams of solution. So this is equal to 2 grams of solute per billion grams of solution. So we can actually use this as a conversion factor. And then we start out with our 250 grams of solution. And those 250 grams of solution contain 2 grams of solute per billion grams of solution. Since the question asks for milligrams, then we need an extra conversion factor here that tells you 1 milligram is equal to 10 to the negative 3 grams. And with that, grams of solute cancel with grams of solute, grams of solution cancel with grams of solution, and we end up with milligrams of solute. So the calculation out of this is 0.0005 milligrams of mercury, which is pretty much 0.5 micrograms. Okay, now that is the mass of mercury that will be contained in that glass of water. It's a very, very small amount. So you're comparing 0.5 micrograms, which is 0.5 times to the negative 6 grams, versus 250 grams of solvent, well, of solution. So it makes no difference. Adding 0.5 or subtracting 0.5 micrograms from 250 makes no difference. So the contribution of the solute to mass of the solution is negligible. So you just don't consider it when you're using ppvs, ppms, and ppts. Another concentration that we will be using is the molality, and I want to stress the difference here. So we are looking at molality versus molarity, and the difference is right here. In molarity we have an R, in molality we have an L, and the meaning is quite different. Molarity is going to be moles of solute, of course, per liter of solution. But when it comes to molality, well, we keep the moles of solute, but our denominator is kilograms of solvent. So that is the most important difference between molality and molarity. And why we use molality? Well, one of the things that molarity, or one of the problems that we have with molarity is that it's temperature dependent. Why is it temperature dependent? Because volume of matter depends on the temperature. So if you increase the temperature, usually the volume will increase, the matter will expand, and therefore if you change the volume, you change the molarity. When you want to work with something that has a more constant, if you will, value of concentration, then you go to molality, because you have number of moles. The number of moles will not change with temperature, and per kilogram of solvent, the mass of solvent will not change with temperature. The volume will, the mass will not change with temperature. Okay? And remember, this is solvent, not solution. So that's one of the main differences here. Okay? With molality. Now, how do we use molality in a problem? So, and this is rather simple. We have sodium chloride. We have 29.5 grams of sodium chloride. And we need moles, right? So we need to convert these to moles. 1 mole of sodium chloride is equal to 58.44 grams. Therefore, grams cancel with grams, and we obtain 0.505 moles of sodium chloride. Now we need kilograms of solvent. We have 212.7 grams of water, which is pretty much, this is a rather straightforward conversion, so this is 0.2127 kilograms of water. So you have molar solvent, you have kilograms of you have moles of solute, you have kilograms of solvent, so molality is going to be equal to 0.505 moles divided by 0.227 kilograms, and this is equal to 2.37 moles per kilogram, or 237 molal. Okay? Now, how about we do this the other way around? So calculate the mass of perchloric acid needed to make 5.13 molar solution in 239 grams of water, right? So we can use this as a conversion factor, because this, after all, is 5.13 moles per kilogram. So if we start with 239 grams of water, first thing to do is to convert to kilograms, and then we can multiply by the molality, so 5.13 moles per kilogram. So we cancel here, we cancel here, and then out of this we obtain 1.23 moles of perchloric acid. Okay, and we could have done this in just one go, but 1.23 moles of perchloric acid times the molar mass, which is 100.457 grams per mole, is equal to 124 grams of perchloric acid. So a solution 5.13 molal of perchloric acid in 239 grams of water contain 124 grams of perchloric acid. Another concentration that we are going to use, and this probably you are already familiar with it because you used that in gases in the previous class. This is mole fraction, and mole fraction basically is the number of moles of a solute divided by the total number of moles. And in this case, probably an advantage or not, but the thing is, it doesn't matter how many components you have in that solution. The total number of moles will be equal to the sum of the number of moles for each component in that solution, which is what we have here in this expression. It doesn't matter how many components. If you have 100 components, well, then there is 100 number of moles that you have to add together. Okay, so for any given substance, the mole fraction is going to be the number of moles for that particular substance divided by the total number of moles. One important relationship that you need to be aware of is that, again, regardless of the number of components, if you add all the mole fractions from all the components, they have to add to 1. Okay, if it's only A and B, then mole fraction of A plus mole fraction of B have to be equal to 1. It doesn't matter how many components you have there. So in this one, we have to calculate the mole fraction of methyl alcohol, also known as methanol, in ethyl alcohol, which is also known as ethanol. Okay, so how do we calculate this? Well, we have number of moles of methanol, which is 146, and we have number of moles of ethanol, which is 219. So the mole fraction of methanol is going to be equal to 146 divided by 146 plus 219, and this is equal to 400, sorry. And for the next one, you can do it in one of two ways. You can say that the mole fraction of ethanol is equal to 219 divided by 146 plus 219, which is going to be 0.600. Or you can say that the mole fraction of ethanol is going to be equal to 1 minus the mole fraction of methanol, which is 1 minus 0.400 equal 0.600. It's up to you how you're going to do it. You are going to obtain the same result. So in summary, these are the units that you are going to use. Okay, and notice that molarity, molality, and mole fraction, they all use moles of solute on top, but they differ in what's at the bottom of that fraction. For molarity is liters of solution, for molality is kilograms of solvent, and for mole fraction is the total number of moles. Okay, they use all of the same, but they have a different denominator. Now in the other ones, percent by mass, parts per million, parts per billion, parts per trillion, they all use the same fraction, the same ratio, grams of solute to grams of solution. Okay, what the difference here is what is the multiplier. For percent by mass is 10 to the power of 2, parts per million 10 to the power of 6, parts per billion 10 to the power of 9, and parts per trillion 10 to the power of 12. Okay, that's the difference. Now, one other thing that you have to consider when using these units, percent by mass, ppms, ppbs, ppts, is that you are using a mass ratio. So you don't have to settle for grams every single time. As long as you use the same unit of mass, then you can express your percent by mass or any of the others in pretty much the same way, and you're going to obtain the same number. So that means you can do kilograms of solute over kilograms of solution. You can even do pounds of solute over pounds of solution. It doesn't really matter. Even if you try to convert that to grams, the conversion is going to be the same, and being a fraction, being a ratio, that conversion will cancel anyway. So as long as you have the same units of mass for both the solute and the solution, you're going to be fine. The number that you are going to obtain is going to be the same regardless of the mass unit that you are using. Couple other equations that you are going to need when working with this. Moles equals mass over molar mass, and density is mass over volume. Okay, you also need the mass of solution equals mass of solute plus mass of solvent, and that comes very useful because this is where the fun begins. Now the main goal here is to convert between concentration units, and so that you have to convert. If you are going from moles to grams, well, you have to use the equation number of moles to convert, to make the conversion. And if you are converting between solvent and solution and moles, well, you need all that information to play a role so that you can convert between these units. So let's go for this one first. We want to know what is the molality of a solution of methanol in water that contains a mole fraction of 0.133 of methanol. Now, one thing that you have to keep in mind with your concentration units is that they are intensive properties. They do not depend on the amount of solution that you have. The concentration will not change if you increase the amount of the solution. Okay? So that means that gives you room for assumptions. And what do I mean by assumptions? Well, you have the mole fraction, but you don't have any starting point like an amount of solution, an amount of solute. You just have the concentration. So this is actually pretty simple, because if the mole fraction of methanol tells you that it's 0.133, that means there is 0.133 moles of methanol per every 1 total mole of solution. So you have two components. You have methanol and water. Therefore, the mole fraction of methanol plus the mole fraction of water is equal to 1. Since you have one total mole, then that means mole fraction of water is 1 minus 133, and this is equal 0.867, right? So that's our starting point. You have 0.133 moles of methanol and 0.867 moles of water. Okay, since we are calculating molality, right, we already have our number of moles of solute, so we don't have to do anything else with that. But we need kilograms of solvent, and water is the solvent here, so we need to take these 0.867 moles of water and convert that to kilograms. So 0.867 moles of water times 18.14 grams of water per mole. We cancel moles here. This is grams, so 1 kilogram is 10 to the power of 3 grams. Well, that gave us 0.0156 kilograms of water. So we have our kilograms of solvent, we have our moles of solute, therefore molality is 0.133 moles divided by 0.0156 kilograms, and this is equal to 8.53 molar. Okay, so a solution with a mole fraction of methanol equal to 0.133, it's equal to a solution 1.53 molar in methanol. Now in this case, we also want to know the molality of the solution, but in this case we have the molarity, not the mole fraction. So how do we address this? So we have the molarity, we need to know the number of moles of solute. So how about we determine how much phosphoric acid we have in that molar solution, right? So again, we only have concentration, we don't have a starting point here, but since this means 14.8 moles of phosphoric acid in 1 liter of solution, then that's actually our starting point. We have 14 moles of the acid, right? So here 14.8 moles of phosphoric acid times 97.99 grams of phosphoric acid per mole of phosphoric acid give us a total of 1450 grams of phosphoric acid, which is the solute. Okay? So why do we need this? Well, we are calculating molality, and molality is the number of moles of phosphoric acid, which we already have. We have 14.8 moles. We calculated the mass of the solute because we have volume of solution. If we take the volume of solution, which is equal to 1000 milliliters, then we can do 1000 milliliters times 1.685 grams per milliliter, which is the density of the solution. Okay, now it's not the water, it's the density of the solution that you have here, and this is equal to 1685 grams of solution, right? Its molality, we need the kilograms of solvent. So our solvent is going to be equal to your mass of solution minus the amount of solute, right? 1450 grams of solute. And this is equal to 235 grams of water, right? Since this is 235 grams of water, this is equal to 0.235 kilograms of water. Okay? Now with that information, we have our number of moles up here. We have our kilograms of solvent down here. Now we can calculate molality. Molality is going to be equal to 14.8 moles divided by 0.235 kilograms, and this is equal to 63.0 molar. Okay, so that's how you use these units, these concentration units, and how you can convert between units depending on the information that you have. Okay, so remember here, it's about remembering what each one of these units mean. What are the numerators? So what is your measure? How are you measuring your solute, and how you are measuring either the solution or the solvent? So there is a dependence between those two and the meaning that those units have. Okay, so we need all these units because the next step is to determine the colligative properties of solution, and well, they are not all of them use molarity. Some of them will use the mole fraction, some of them will use the molality, and we need to be familiar with these concentration units in order to be able to calculate those properties of the solutions. Okay?